Welcome again to another Prof. Scangrella. Today we're looking at current, voltage, and resistance. Again, current, voltage, and resistance. So last time we defined electrical energy and we looked at electrical current. So I'm going to start with drawing a simple electric circuit. So let's start with the electric circuit and start with a symbol for a battery. And let's add a symbol for a load. Okay, so this is a DC power source. So this is the symbol for DC power source. And of course, today we will also look at the difference between DC and AC, or alternating current and direct current. So again, last time we established that, let's change my color here. We established that we have a voltage present here. So say this is the battery, and maybe we have a couple of batteries together, and so this is giving us 12 volts, right? This is going to cause current to flow, and of course we saw that the electrons, as the electrons are moving, each electron has a negative charge, and so based on the amount of electrons that are moving per second, we will get our current, right? So we said the electrons move from the negative to the positive terminal, right? And based on the number of electrons that move, we get the number of charge that is moved. And so current is going to be the rate flow of charge. So let's start with defining current. Current is the rate flow of charge. All right, so in other words, we can define it, we can write an equation for current. I is going to be equal to Q over T. Current is going to be charge over time, right? All right, that is current, charge over time. And again, that charge is based on the flow of electrons, because each electron will have each electron will have negative 1.62 times 10 to the minus 19 coulombs, all right? So voltage, we said the voltage causes the current to flow, right? So let's go ahead since we know what current is, and we also give an example that if you have a circuit and you were told that if you're measuring here and the instrument you use to measure current is called an ammeter. So I'll just write the name here. If you have an ammeter and you're measuring the amount of charge that is flowing, and you see that you have, say, 1.5 coulombs of charge per second in 1 second, then you know that the current is going to be 1 ampere, right? Okay. So the next thing we want to describe is we want to discuss voltage. What is voltage, right? How do we define voltage? Voltage is, or can be defined as, the energy available or the energy moved energy available, energy moved. You can also say the work done per coulomb of charge. The work done per coulomb of charge, right? Okay, how do we explain this? Right, again, these electrons that are moving, we're saying that if there's a load in the circuit, they're going to convert that energy into one form. So this is a resistor here. And this resistor, what it does, the job of it is to convert electrical energy into heat, right? So it converts electrical energy into thermal energy. That's the job of this resistor. So the energy from the battery is going to be converted into heat via this resistor, right? If we had a light bulb here, the energy would be converted into light, right? So voltage tells us the energy that is available per coulomb of charge, right? So if we have a lot of energy available per coulomb of charge, the voltage is going to be higher. If we have a smaller amount of energy available per coulomb of charge that flows, the energy will be lower. So equation for voltage is that voltage is equal to W here for work done or for energy over charge, right? And again, with voltage, the reason we have the potential as well, the energy available, is because voltage exists even though we don't have a current, right? In the circuit here, we have the circuit is closed, and so we have a current that is established, and so we also have a voltage across the battery. But if there is no closed path, we will have no current, right? But the battery still has a voltage across it. The battery still has the potential to do work per coulomb of charge, right? It still has the potential to do work if it is connected in a circuit. So voltage is the energy available or the work done per coulomb of charge that flows, right? So let's give you an example. If say in our circuit up here, if we had if 5 joules of energy if 5 joules of energy was converted to heat, and if 5 joules of energy was converted to heat and the total charge moved was 10 coulombs, what is the voltage? All right, so of course it's just going to be a substitution here. We're going to put the energy 5 joules over 10 coulombs, and that gives us 0.5 volts. All right, so again, voltage is just the energy available per coulomb of charge that flows. Again, the voltage is what pushes. We said the voltage is one way we can have free electrons, right? Voltage causes electrons to flow in a particular direction. Of course, we say that the electrons are being repelled from the negative terminal and they're going towards the positive terminal. The voltage will cause these electrons to gain energy and to become free electrons. So we have these electrons moving throughout the circuit. The last thing we want to discuss is resistance. What is resistance, right? So again, we already said that a resistor is a device that converts electrical energy into heat. Right, a resistor is a device that converts electrical energy into heat. You will see that resistance is simply the opposition of the flow of current, right, or the movement of charge. All right, so I'll start right here. Let's go to the next page. So resistance, this is going to be the opposition. It's a measure of the opposition to the flow of charge of electrons. All right, we also say it's the opposition to the flow of current. Again, the flow of current is the flow of electrons, which is measured as the flow of charge. So opposition, this resistance is the opposition to the flow of charge. Now, what causes resistance is based on a number of different factors. Resistance is based on, and we can just change my color right here. Resistance is based on the resistivity of the material. So the material has a resistivity which is inherent to that material. So put resistivity. All different materials have different coefficients of resistivity. Resistance is also based on the length of the material. So the longer the material, the more resistance is going to have as well. And the cross-sectional area of the material. Right, all of these things determine the resistance of a particular material. Again, the length of the material, the resistivity, and the cross-sectional area. We actually have an equation that we can use to calculate the resistance of any material. Temperature coefficient, that is, as the temperature increases, the resistance of that material will increase, and vice versa. Right, so again, resistance is the opposition to the flow of electrons, or the flow of charge, the flow of current, and the unit for resistance is the ohm, and the symbol for resistance is the omega. So you will see the omega for ohms, right? We also measure the opposite of resistance. Sometimes instead of describing the resistance for a circuit, it's important to describe the conductance. And conductance is simply 1 over resistance, right? The opposite of resistance. So again, sometimes it's important to measure the conductance or to express the conductance, and we simply take the opposite of resistance. So if we have a resistor that has a resistance of 10 ohms, then we know that the conductance is going to be one over resistance, which gives us 1 over 10, which is 0.1 Siemens. The unit for conductance is the Siemens. All right, so again, resistance, the opposition to the flow of current. Conductance is the opposite of resistance. It actually tells us how much current is flowing. Voltage, we said voltage is the energy that is available for every coulomb of charge that flows. Of course, if you have higher voltage, you have larger amounts of energy available per coulombs of charge that flows. And current, we already described, is the rate flow of charge, right? When we close the circuit, the electrons are flowing. We're actually measuring how much charge is flowing per second, and that is our current. Now that could be a large number, it could be a small number based on the voltage that is present and the resistance that is present. In our next session, we'll look at Ohm's law that relates voltage, current, and resistance. This is Prof. Scangrella signing out. Hope to find you on the next one.